In the first 2 episodes, we built the smallest possible network. One linear layer, a single output unit, feeding a sigmoid and binary cross-entropy. We derived its gradient by hand, and we watched the residual appear, the prediction minus the target. Then we backpropagated it, and we checked every number against a finite difference. So we now have a machine that learns 2 classes, and a backward pass we actually trust.
But 2 classes is the easy case. Surely 3 or 10 classes needs a whole new model and a whole new backward pass.
That is the natural fear, and it is wrong in the most satisfying way. Going to K classes is not a new model. It is the same model grown sideways. Instead of 1 output unit, we give the linear layer K output units, 1 score per class. The body does not get deeper, it just gets wider. Look at how little changes in the code. Before, we wrote the network as a linear layer from 2 inputs to 1 output, with sigmoid and binary cross-entropy. Now we write a linear layer from 2 inputs to K outputs, with softmax and cross-entropy. That is the entire structural edit. Widen the output, do not deepen the network. It is still 1 linear layer, still just weights and a bias, still computing a plain list of numbers. So the body now hands us K raw numbers, 1 per class. We call them logits, and on their own they mean nothing. The softmax is what gives them meaning. It exponentiates each logit and divides by the total, which forces every value positive and makes the whole set sum to 1. K logits become K probabilities. Here they are as bars. The network is most confident in class 1, less sure of class 2, and least of class 0.
And once we know the right answer, how do we score that?
With cross-entropy, which is just your surprise at the true class. In the code, the value method reads beautifully, the log sum of exponentials of the logits minus the logit of the true class. That single line is exactly the negative logarithm of the softmax probability you placed on the correct class. Confident and right costs almost nothing. Confident and wrong costs a great deal. And notice the spine has not moved. It is the same shape we have kept since the very first unit. The body computes numbers, the head decides what they mean. Swap sigmoid and binary cross-entropy for softmax and cross-entropy, and the same stack of layers turns from a yes or no classifier into a many-way classifier, without touching a single weight. Now the moment this whole episode is built around. What is the gradient of softmax cross-entropy with respect to the logits? In the code, the grad method does 3 small things. It computes the softmax probabilities. Then it subtracts 1 from the entry at the true class. Then it returns that vector. Read it out loud, and it is the vector p minus the 1 hot indicator of the true class. It is the residual again. Prediction minus target. Only now, instead of a single number, it is a whole vector.
Alright, the loss gradient is a vector now, but the backward pass has to change to handle a vector, right?
Here is the backward pass. Read every line. It takes the gradient from the loss, then it walks the layers in reverse, handing each one the gradient and getting back the gradient for the layer below. There is nothing in here that knows or cares whether the loss handed it 1 number or 10. Not 1 line changed from episode 2. That is the payoff we earned 2 episodes ago. We derived the backward pass once by hand and verified it, and now it just works for K classes for free. We did not rebuild it, we reused it. And this is the mechanics living underneath inductive biases, episode 2, where the claim was that the loss is a distribution assumption. There, you were told that softmax cross-entropy is the categorical likelihood. Here, you see the code where that assumption makes the gradient fall out as nothing more than the residual. There is exactly one thing that gets genuinely harder with K classes, and it is not the math, it is the arithmetic. A naive softmax exponentiates each logit directly, but logits can grow large during training, and the exponential of a large number overflows. The value e raised to the power of 1,000 is not a big float, it is infinity, and then you divide infinity by infinity and get nonsense. A correct formula, wrong on the hardware.
So do we clip the logits or scale them down somehow?
No, and that is the elegant part. We do not have to change the answer at all. Subtract the largest logit from every logit before exponentiating. Call that largest value the max. Because that same shift appears in the numerator and in the denominator, it cancels exactly, so the probability is identical to the penny. But now every exponent is at most 0, so every exponential lands between 0 and 1. It can never overflow. And this is why the real code carries the max subtraction in 2 places. In log sum of exponentials, we pull the max out front and add it back after the logarithm. In softmax, we subtract the max before exponentiating. Same value provably, safe value always. It is one of those rare tricks that costs nothing and buys everything. So let us actually run it. 3 Gaussian blobs, 3 classes, and a single linear softmax layer trained on them. The network carves the plane into 3 regions that meet at a seam, 1 region per class. And this is not a toy ceiling. The very same head scales straight up to real data. The 8 by 8 handwritten digits, 10 classes, a linear layer from 64 inputs to 10 outputs. Same softmax, same cross-entropy, same everything.
But how do we know the vector gradient is actually right and not just plausible?
The same way we have known since episode 2. We do not trust a gradient we have not checked. We call gradient check on the K-class network. It takes our hand-derived gradient from one backward pass and compares every component against a central finite difference of the loss, nudging each weight up and then down, and watching how the loss responds. And here is the card. On top, the analytic gradient straight from our backward pass. Below it, the numerical gradient from finite differences. The worst relative error between them is about 1 part in 10 million. It passes. So the claim that the K-class gradient is just the residual is not a slogan we are asking you to take on faith. It is a passing test, in green. Same residual, same backward pass, now across K-classes. Next time we stack layers and the network finally gets deep.